Hello everyone, this is Mrs. McCreary. Thank you for joining me with the Wittenberg Academy geometry class. Today we are going to be starting at the very beginning of our book, a course in geometry, a course in plane and solid geometry. We're also going to be doing some comparisons with Euclid's elements. The very first thing we're going to be discussing, as seen on page 1 of your textbook, is this idea of inductive and deductive reasoning. So inductive reasoning is what we do all the time. It's when you are given, you take your observations and you come up with general conclusions. So something is going on and you say, well, clearly that's what's happening, and you're basing that just on observations. Now, deductive reasoning takes it a step further, and you look for rules to support those reasons using if-then statements. So your book has a few examples. On page 4, there's example 2, and it says, 3 coins of the United States have a total of 60 cents. Can you deduce the names of the coins? Okay, so inductive reasoning, you say, 3 coins, 60 cents, okay, quarter, quarter, dime. Very easy. Inductive reasoning, you're just using your observations and coming up with, whatever is around. So deductive reasoning, we have to use our if-then statements. We have to see if we can come up with proof. This is definitely where any logic study that you've had in the past is really going to come in handy. And if you haven't done much study of logic, this is geometry. Proof geometry is kind of a primer of formal logic because it does follow a lot of the same steps. So again, looking at number 2 on page 4, 3 coins of the United States total 60 cents. Can you deduce the names of the coins? So in this case, you could come up with almost like a truth table, filling out, well, I know, these are the values of all the coins, and come up with all the different combinations that would equal 60 cents. That would be an example of deductive reasoning. Number 3 says 3 coins of the United States have a combined value greater than 70 cents and less than 80 cents. Can you deduce the name of the coins if no 2 of them have the same value? So again, our text is asking us specifically, for deductive reasoning. So we, again, are looking for some proof, so we would come up with a table to support our information. So really the big distinction that you need to remember between deductive and inductive reasoning is that in deductive reasoning, you have to have that proof. Either there's a mathematical rule or a geometric postulate or theorem, or an if-then statement that you can use to support your reasoning. So now let's look at page 4, number 6. It says, can a deduction be made about Tom from the statements that follow? So here we're given statements. And in geometry, they're just called the given statement. That's what you start with. So all dogs have 2 ears. Tom is a dog. So we can look at that first statement, all dogs have 2 ears, and change it into an if-then statement. If Tom is a dog, then he has 2 ears. That fits our statement. So we can deduce something about Tom in 6a, that he has 2 ears. Now 6b, all dogs have 2 ears. Tom has 2 ears. So on the surface, it looks like using inductive reasoning, we could say, oh yeah, Tom's a dog. But using our deductive reasoning, we can say, yes, but, people have 2 ears, and cats have 2 ears, and hippopotami have 2 ears. So there are a lot of other examples. Just like in logic, you can't necessarily work both backwards and forwards. With the deductive reasoning, you have to make sure your statement supports itself. All right, so now C, we have all dogs have 2 ears. Tom has no ears. So if Tom has no ears, then he can't be a dog. That follows. All right, so for our live chat, I want you to look at the rest of those examples on pages 3 and 4 and just be prepared to defend some of your reasonings, some of your proofs, some of your if-then statements for our discussion. All right, another important topic that the beginning of our text focuses on is definitions. And we are talking specifically about definitions in written form. So as you can see, the book gives the definition of a definition as the meaning of a word given in a sentence. So as you can see, none of my definitions are actually technically, according to the textbook, definitions. But we have the benefit that I am here to explain what these little segments mean, whereas if you're just reading a text, you don't have that help, so it needs to be given in a full sentence. So some of the qualifiers of a good definition as listed on page 5 is that A, it's a sentence, which again, mine aren't, but we have me explaining them. Lucky you. Okay, so the second part is that the term is named in class. What that means is there's a part of the sentence or a part of the definition that says, this is the word we're talking about. All right, and it kind of fits with these things that you already know. Then the next part that a good definition does, it's going to explain the term. So we have our definition of a particular word. It fits in this category. This is what it means. Number 4 is an important one. A definition needs to be easily understood. It has to be using words that you already know, words that have already been explained, and words that don't just lead back to themselves. There's a good illustration of that on page at the bottom of page 6, where it talks about those circular definitions. You can't say that the example they use, that placid means calm and calm means placid, because that never really gets you anywhere. So you have to make sure you're using words that you understand and that your audience understands, and that if those are words that are technical or specific, they've already been explained. For example, in geometry, it wouldn't be useful to say that an interior angle is the measure of an angle inside 2 rays if you don't know what interior or ray or angle mean. So always making sure you're using words that have already been defined or that are commonly understood. Now in math, sometimes we use words that are commonly used in regular speech, but they don't always mean the same thing. For example, the word and. And can mean a lot of things in normal life, but often in math it specifically means addition. You know, if we have 4 and 5, then we're talking about the quantity of 9. So we have to be careful with the words that we use and make sure we're using them in a specified way. And also, and a definition should not have unnecessary qualifications. We shouldn't have, well, this is a term if it does this, and if it does this, and if it does this, and if it does this, if those aren't needed. We should make them as simple and concise as possible. And therefore, they should also be reversible. Just as I can say a definition gives us the meaning of a word in a sentence, I can also say a sentence that gives us the meaning of a word is a definition. I shouldn't have to say a sentence that gives us the meaning of a word is a definition if it explains everything in clear terms, and there is a semicolon used, and there is a compound subject, and there is a list of prepositions. Those would be unnecessary qualifications and may or may not actually have anything to do with what your term is. So there are some examples on page 6, some exercises. The first one that I would like to discuss is number 1. It says, if a person knows no Arabic words, is it possible for him to learn the meaning of an Arabic word from an Arabic dictionary? Again, with these, look through all of these exercises. We'll discuss some of them, more of them, in our live chat. So in this case, number one, if you don't know any Arabic, you can't really look up anything in an Arabic dictionary because everything is in Arabic. Um, that's why there are Arabic to English dictionaries or any other particular language. But just like, any language, if you go in and you start looking at the words and you have no basis, that really there's nothing to help you. So that goes to the fourth criteria for a good definition is that it's easily understood using terms that you know. All right, and then another one that I want to talk about is number 3. Give a definition of an even number or an even game. So an even number is a number that can be broken into pairs with no outlying numbers. Okay, so an even game could be a game that has clear rules allowing everyone the same opportunity of winning. Or you could even define it as an even game if you're talking like a sports game. An even game is one with the same amount of players on each side. So even with that, there are multiple definitions. Again, we'll talk more about some of these exercises in our live chat. So those are just some things you need to keep in mind as we study through our whole term. We want to always be using deductive reasoning, having if-then statements, rules, proofs, supporting material, supporting ideas for anything that we are working with, so that way we know that we're not just saying something because it appears true. Okay, so, for example, if I said, well, I have 4 pets, Boris is a cat, and Vladimir is a cat, and Genevieve is a cat, and I also have Klaus, you would have your inductive reasoning that maybe Klaus would be an additional kind of pet, or, what kind of pet Klaus is, and we'll talk about that more at our live chat. And if not, then if you're not watching this before the live chat, we'll have already talked about it. All right. So now some specific terms that are going to be necessary as we study geometry. These again are the basic terms that we're going to be starting with. Let me change my pen here. Okay, so a point. In our text, they discuss a point as kind of just a location in space. It doesn't have any dimensions. It doesn't have any length or breadth or width or anything to determine it. It is, infinitesimally small, but we need to be able to talk about things in space without placing a circle there or placing a square there. So we have come up with the point, which we write often just as a dot, as a period. Not that it takes up that much space, but just so that we can identify it. And in a point, we will label that with a capital letter. Okay, so we can also, if we have 2 points, we can then connect them. Better than that, usually they'll be connected with a straight line. Yes, I'm sorry. So 2 points connected is a line, and unless otherwise specified, it should be a straight line, meaning 180 degrees on a protractor. I, however, am not that good at drawing, so you're just going to have to bear with me on that one. So when we're discussing a line is just a distance. It doesn't have any width, as a rectangle would have both length and width. It is just that length. So think of it, it's, again, so string or hair or something like that does have width, but think of it more of that way. And that way is a string covers length, but it doesn't really cover distance. It does, but we're kind of going to pretend that it doesn't. In geometry, there's a lot of pretending. We've marked a certain location in space with this dot, although that location doesn't actually take up any space. We just need a way to discuss it. a line. Clearly the line that I drew has some width or breadth to it, but we're pretending that it doesn't. So the line can be discussed either as line AB, or it can be discussed as just, we could label it with a lowercase letter of D. So it can be line AB or it can be line D. And that distinction between the capital and the lowercase helps to give an idea of what we're talking about. So a plane is a two-dimensional surface, and they can have, infinite length and infinite width, but it's just two dimensions. Kind of like a piece of paper that goes on forever, or a chalkboard that goes on forever in all directions, or a computer screen, or something like that. Now again, we can talk about specific planes or specific areas of the planes based on lines that are included in the plane. Here we have line AB, line BC, line CD, line DA, or the points that are included in the line, point A, B, C, and D. All of those are just there, but since they are all on the same plane, we can use those points to help discuss which plane we're talking about. And again, just like a line, we can also refer to a plane with a lowercase letter. Space is a little bit more difficult. It is discussing kind of everything. So if we are talking about space, that is all length and width and breadth, and then we will need to define a specific area within that space, such as line DC, or something like that, or plane M, or line D, those kinds of things. Now we can also have angles being those areas where two lines intersect or two lines meet at the same point, and those will have a measure, and we write those with that curved line in most cases. We'll talk about times we don't later. And so that is an angle. It's just a point where two lines intersect. Our book also discusses angles being two rays that have a common point. Now a ray is like a line in that it has an endpoint, so we'll call this endpoint E, and then it continues. So when lines continue, we draw these arrows on them. When they don't, we draw the points where they end. So in this case, this is ray E, and we would denote that with an arrow over it, whereas up here we have line AB, and we would put a line over the top, so that way we know we're talking about a line versus a line segment or a ray. Now we have these two rays coming out of E. The space between them again is an angle. We'll call it angle F. Actually, we call that angle E. We could, if we needed to, if we had this over here, call this one angle F and angle G. Also, there's generally other points on a ray. So here we would start with the vertex. The point where they come together is always going to be in the middle. So this we would denote as this little symbol here that looks kind of like a flopped over L is going to be our angle symbol. And we start with G, E, H. Angle H, E, G is also the same angle. G, E, H, H, E, G. So when you're given information like this, it's kind of like connect the dots. So you find point H, you find point E, you find point G. Now when we're given H, E, I, that is then this angle. Or it could also be written as I, E, H. Those are the same angles. So that is this angle right here. And of course there will be much more discussion of this at later points. And it is also discussed on pages 9 and 10 in your text. Now, all of these things so far are one-dimension or two-dimensional items. We can also have three-dimensional items that have length and breadth and width, and that would be a solid. So let me come over here. And we would have something that has on one plane A, B, C, and D, and then on another plane there is point E, and they all come together to form this very poorly drawn triangular prism. Or no, this is a triangular prism. Okay, so at this point we could call this a triangular prism ABCDE, or we could give it a specific name. You can see that the lines that we would be able to see, although again this isn't well drawn, are given solid lines, and the lines that would be covered up if it were a like an opaque or solid colored object are given in that dotted line. You can see that line AB is in a dotted line. So those are, I guess, the basics of geometry. Just again going over some of those ideas. So we have point A that is on line AB, and we're actually going to make it ray AB, and then we also have ray AC, creating angle BAC, which is here. We have them all contained within the plane of A, B, C, D. Again, not well drawn, but it's still there. And then coming up, and then where all of these lines cross are the vertices. The actual outside point is the vertex, or the multiple or vertices, and then the interior would then be the angle. And then if we excuse me, discuss another point that is on a different plane, E, we can make a solid object by bridging that distance between those planes. All right, so if you have any questions, let me know. Again, we will be discussing the exercises on pages 3, 4, and 6 in our live chat. Please complete the exercises on pages 11 and 12 that are listed on your page. And if you have any questions, there are the forums, or you can email me, and otherwise I will talk to you at the live chat. Good luck, and thank you for joining me.